Okay. Okay. That should be better now. Let's test it. I can hear myself. Not yet.
Okay.
Yep. Okay. All right. So 2015 number 3. 2015 number 3. This is a good one. This is a good one. Yeah. So I know exactly what the problem was actually, and I've run into this before. It's when I'm charging the receiver for my my wireless setup from the computer. And for those that are interested in electrical engineering, this is actually what's called a ground loop. And that's why you had that kind of interference. Okay. So to start with, somebody asked me to do number 3 from 2015. And so this problem is one of these problems where you have some distribution of charge that's over the arc of a circle. And what you want to do is you want to find, I believe, the electric field. Find the electric potential, actually, so it's a little bit easier than finding the electric field, at some point x is equal to a. So with this problem, where we're going to start is to say that we have this charge that's spread over this arc of a circle. This is some charge of capital Q. So some capital Q that's going to be spread over the arc of this circle. And what we want to determine is what the electric potential function is at the point x is equal to a. Okay? So the way that we're going to go about this is first we can say that there's going to be all these tiny little dq's that are on the arc of this circle. And because it's the arc of a circle, what we can say is that dq in general, and this is also true for line distributions of charge, dq is equal to lambda dl. And specifically for the arc of the circle, this has some radius that is probably given as some radius of capital R. So what we can do is we can say that dl is going to be r d theta. And lambda, we remember that lambda is by definition the charge per length. And so this is going to be the total charge that's spread over the arc of this circle divided by the length that it's spread over. And so this is going to be half a circle. And because it's half of a circle, we can take the circumference and divide it by 2. And that's going to give us a length or a distance of pi times r. So that says then that dq is going to be q d theta divided by pi. We just cancel the r's. And then ultimately the equation that we're getting at here says that dv is equal to 1 over 4 pi epsilon naught dq divided by r. So we already have what dq is. We just need to find out what r is. And so this is where this kind of departs from other questions that we've had where we've had arcs of charge, because for those problems we always wanted to find what the electric field or the electric potential is at the center of the circle. But this one's a little bit different because what we want to do is we want to find it at some point x is equal to a along the x-axis. And so in order to do that, what we need to do is we need to figure out what this r is. Okay? So to find what this r is, the first thing I'm going to do, I'm going to get rid of this, this capital R here. I can put it down here. The first thing that I need to do is to get some kind of right triangle here where I can write r as, I can find r with the Pythagorean Theorem. And so in order to do that, what I'm going to do is I'm going to say that this is some distance r that connects this from the origin to the arc of the circle, and there's some angle theta here. Okay. So now when we look at this, there's going to be some y portion here that can be represented as the r times the cosine of theta. And there's some x portion here that I can find to be some r sine of theta. Okay? So then what I can do is I can say, well, this makes a right triangle. So I have my right triangle here. And then I just need to put together the pieces that I have in the y direction and in the x direction. So in the y direction, this is going to be some r cosine of theta. In the x direction, this is some r sine of theta plus the distance a. So then what I can do is I can put that together using the Pythagorean theorem to find what r is. And that's just to say that this is going to be r cosine of theta quantity squared plus r sine of theta plus a quantity squared. Okay. Now I'm gonna do some algebra here in order to simplify this a little bit, and that's just going to say that I'm going to expand this portion right here, and I'm going to expand this here. So that's to say that this is going to be equal to the square root of r squared cosine squared of theta plus r squared sine squared of theta. And when I have this sum of two things under a square, I'm just foiling this. So this is going to be plus 2a r sine of theta plus a squared. And you might be wondering why I'm doing this, but here's the punchline. We know there's a particular identity with sine squared and cosine squared such that cosine squared theta plus sine squared theta is equal to 1. Okay? So from these two terms I can factor out an r squared, and then I'm going to be left with cosine squared plus sine squared, which is just 1. And so this is going to be equal to the square root of r squared plus 2ar sine of theta plus a squared. And that's what r is in this case. Okay? So to put this all together to define what the electric potential at this point is just to say that V is going to be equal to 1 over 4 pi epsilon naught times this q divided by pi, so that's going to give me a pi squared epsilon naught times q times the integral of d theta times 1 over the square root of r squared plus 2ar sine of theta plus a squared. Okay. Now we need to look at the limits and ask ourselves in terms of why is it r cosine of theta? Why is it r cosine of theta? So the y component is going to be r cosine of theta because let me draw this again right here. So this is the angle theta that I'm defining. And the portion that's in y, because this is the adjacent side, this is going to be r cosine of theta. And the opposite side is going to be r sine of theta. Okay. Ask me again if that doesn't clarify it, but that's basically why I had the r cosine of theta and the r sine of theta. And ultimately what I'm doing is for the x distance that I am from this, it's going to be r sine of theta plus a, because a is the distance here, and the r sine of theta is this distance. So that's ultimately why that is. And again, why isn't it not negative? Ultimately, it's not a vector. It's not a vector, right? So you could say if I wanted to find some electric field here, the electric field would have some negative component, and so the unit vector r hat that points from here to here, I would have to define some different angle here. Call this phi. R hat would be equal to this would be cosine of phi x hat plus sine of or minus sine of phi. So this is the portion that you're worried about. This is minus sine of phi y hat. But here's the punchline. Because we're trying to find the electric potential, we're not actually interested in finding what the vector is. We're just concerned with finding the distance. And so whether you make this positive or negative, it actually doesn't matter because I'm going to square it. So a negative times a negative is going to be a positive. So there is no vector information that I need to carry through here and ask myself, is it going to be positive? Is it going to be negative? it doesn't matter because I'm calculating the electric potential. The electric potential doesn't have this r hat in here, and so I don't really need to worry about the negative signs. When I square it, it comes out in the wash in the end. Okay. So again, hopefully that clarifies things. But if it doesn't, I'll talk about it again. Okay. So now the next part and the last thing that we need to do with this integral is to determine what the limits of integration are going to be, and that's just to say, per the angle that I defined here, where does it start and where does it end? And so this starts at theta is equal to 0, and it goes to theta is equal to pi. Okay. Now the second part of this problem, if I remember this one correctly, the second part of this problem asks what is the value of the electric potential if we say that A is equal to 0. And so in that case, what we do is we can take the equation that we have, and everywhere we see an A, we can set it equal to 0. And so when we do that, this term goes to 0, and this term goes to 0. And so this is going to be V is equal to 1 over 4 pi epsilon naught, 4 pi, the pi squared, times Q times the integral of 1 divided by R, right? Because we have an r squared under the radical. When we set this is 0, this is 0. This is just going to be 1 over r d theta from 0 to pi. Okay? And then when we evaluate this, this integral, 1 over r is just a constant. So this is the integral of d theta from 0 to pi. That just gives us a factor of pi. And so in the end, what we end up having is that this is going to be v. The pi is going to cancel one of these pi's, and so this is going to be v is equal to 1 over 4 pi. We have a q in the numerator, and an epsilon naught r in the denominator. And that's our final answer. Okay, perfect. So you understood what I said last time. Okay, so that's it for this one. So again, this one's it's a little bit different than some of the questions that we've done before, but it follows the same spirit. And the thing that really makes this one a little bit more complicated than any of the other ones that we've done is defining what R is. And to go back to some confusion that was had before, we don't have to worry about whether it's positive or negative. We're trying to find R. R is just some magnitude. And so that means that what I can do is I can break these triangles apart. I can find what the x portion is. I can find what the this is the y portion, and this is the x portion. And then square them, and then take the square root, and that gives me what R is. That was really the trickiest part about this one. And then the last part is just saying, well, what happens if A is equal to 0? And that reduces back to the same kind of question that we had done before. Okay. Number 4 from 2017. Okay. And as I'm going, if you guys have questions that you want me to answer, go ahead and just post them in there, and I'll go through these as we go. So number 4 from this was a pretty common one. This is it's a very important question too, because what this question is getting at is the table that I had written in the last. On the last page of one of the chapters. It was the electric potential chapter. And that is how do I relate all of these things together? So in the spirit of like the way that I teach this class, I never really like to write an equation and leave you kind of high and dry and say, yeah, it's an equation, just use it. All of the equations have to be related to each other. And this question right here demonstrates how these equations are related to each other. So the table that I had here, we had force, we had electric fields, we had electric potential, we had potential energy here. I'll show my hand a little bit here. I'm not going to ask you anything about potential energy. What I am interested in is the force, the electric field, and the electric potential. And what this problem does is it goes from force to electric field and then to electric potential, ultimately, I think. Yeah, we wanted to find the electric potential function. So the way that we went from force to electric field and vice versa is to say that these are related via F is equal to Q times E. Okay? F vector is equal to Q E vector. To go between electric field and electric potential, we could go one of two ways. If we go from electric field to electric potential, we say that V is equal to the negative integral of E dot dl. And if we wanted to go from electric potential to electric field, this is to say that E is equal to negative grad V. Okay? So we have all of these equations that, that are related to each other in the way that they are related to each other. Now what this problem asks is it says, consider some force where F is going to be equal to Q0 Q divided by, I think it's R to the 6th, and there's a C here. So this is C R to the 6th R hat. And we want to find what V is at a particular point. We want to find V in general if the charge is actually moved to the point AB. So this is moved to the point AB. So the way that this function is written here for the force, that's assuming that one of these charges is going to be at the origin. But the thing that's tricky about this problem, and again, I'll tip my hand a little bit, I wouldn't ask you about coordinate transformations like this. But the spirit of going from force to electric field to electric potential is certainly something that I might ask you. So for this one, the first thing we need to do is go from the force to the electric field. And that's just to say that the force is equal to Q times E vector. And because this is the charge capital Q, that means that to find what the electric field is produced by capital Q, we just divide this by Q naught. And so that says that E vector is just going to be equal to C Q divided by R to the 6th R hat. So we just divided this equation by Q naught to get here. Now the next part that we want to do is we want to go from this electric field to the electric potential. And when we go from the electric field to the electric potential, we're going to apply this equation right here. And that's to say that V is equal to the negative integral of E dot dl. And so in order to do this, what we need to do is define what dl vector is going to be. Okay? So to define what dl vector is, we had two ways to do it. We could do it in Cartesian coordinates, or we could do it in polar coordinates. And that's kind of a question you're going to have to ask yourself if you're approaching a problem like this. But the punchline is, look at what E is a function of. Look at what the vector for E is. Okay? So this one is going to be some E that's varying with radius and points in the radial direction. And so that should clue us in that we want to use dl in polar coordinates. And that's to say that this is r hat dr plus theta hat this is r d theta. R d theta. Okay. So now when we take this electric field, take the dot product between this dl and then integrate, we're going to have an equation that looks like this. So this is going to be negative integral C Q divided by R to the 6th R hat dot R hat dr plus theta hat R d theta. When we take this dot product, we see that R hat dot R hat is 1. R hat dot theta hat is 0. And so this is going to be, and let me factor out some things that are constant here. So this is minus CQ times the integral, and I'm going to write this in an even more suggestive way so that we can evaluate the integral easily. This is r to the negative 6th times dr. Okay. So now we can integrate this with our basic rules for integrating functions or like x to the n. So this would be like x to the minus 6. So we look at the power here, we add 1 and divide that by that same value. So this is going to be equal to minus CQ r to the minus 5 divided by minus 5. This is going to cancel here. And so what we see is our electric potential function, if the charge was at the origin, is going to be V is equal to CQ divided by 5R to the 5th. Okay, so this is our electric potential function if the charge capital Q is at the origin. But now we're shifting coordinates, and this is the part that, like I said, I wouldn't ask you something quite like this, but I'll finish this for completeness. If we move this charge from here to here, we know that for this function as it's written, r is equal to the square root of x squared plus y squared. But shifting this to the point AB changes this, so r is equal to the square root of x minus a quantity squared plus y minus b quantity squared. And so the final answer is going to be, I'll just leave that here. And so this is going to be v is equal to cq divided by 5 times x minus a quantity squared plus y minus b quantity squared to the, this is going to be the 5 halves. This is the fifth, so that's going to be 10. So this is 11 halves. 11 halves. No, what am I doing? What am I doing? This is r, this is to the 1 half. This is 5 halves. This is 5 halves. This is 5 halves. Okay, sorry. Little minor brain fart there. Okay, so that's the answer that we're going to get here. And like I said, the important part of this process is understanding how to go from force to electric field and from electric field to electrical potential. And I wouldn't ask you something about how is it that I shift my coordinate system like this. Okay. All right. So I'll go through the next one. This one already was 4 from 2017. So the next one is going to be 3 and 4 from 2007. As I'm reading this and setting this up, let me know if there are any questions about what I did here. Okay. So 3 and 4 from 2007. 3 and 4 from 2007. Okay. I'm just not going to do problem 4 on 2007. I'm not going to ask you anything like that. So just to tell you why I'm not going to do that. This is a flux problem where you have some slanted surface. So everything that we've done so far is going to be a cube, but this problem, instead of giving you a cube, it gives you this triangular prism. It's a good problem to in your free time later to go through, but I'm not going to spend the time to go through this just because I'm not going to ask a question like that. But I will take a look at 3 and okay. So 3 really it follows the same spirit as the problem that I just did, and that's to talk about how is it that I go from an electric field to an electric potential. Actually, I shouldn't have erased that, but let me write that again. So this is going to be v is equal to the negative integral of e dot dl. Sorry. So this one says that you have some electric field given by E vector is going to be equal to C divided by R to the 4th times R hat. And I'm using the notation I use. Dr. Baskus, the one that wrote this, these exams, used this I vector sub R. It means the same thing, but I prefer the R hat notation. We want to find the electric potential for this electric field. And so that's just to plug this into here. Again, noticing that this is a function of R, and it points in the R hat direction. So the dl that we're interested in here is going to be R hat dr, and then in general there's plus some theta hat term here. We know that's going to be 0 when we take the dot product. And so this is going to be v is equal to the negative integral of c divided by r to the 4th. When we take the dot product between these, that gives me 1, and then this is just dr. So when we do this integral, this is going to be equal to negative c divided by r cubed with a negative 3 in the denominator. The minus signs are going to cancel, so we have minus minus becomes plus. And so our electric potential function is a function of r. Is just going to be c divided by 3r cubed. Okay? Now, that was the first part. The second part is, from this electric potential, find the x and y components of the electric field at, from this electric potential function, find the x and y components of the electric field at any point x, y. That I wouldn't say that's entirely necessary to go backwards from here to here. And I think that's, what you can do, and I think what it's asking you to do, is to say that now I can go backwards. I can, now that I have this electric potential function, I can find what the electric field is by taking the negative gradient of it. But we already started from this electric field. So why not start from here and then just write this, rather than having it in polar coordinates, write it in Cartesian coordinates. And that's to say that in general here, r is going to be equal to the square root of x squared plus y squared. R hat is going to be equal to cosine of theta x hat plus sine of theta y hat, which is equal to x divided by r x hat plus y divided by r y hat. And so the punchline in the end here is to say that I can put these two things together with this equation, and that's going to give me an r to the fifth divided by 2 with an x hat and a y hat. And so this electric field in the end is going to be c divided by x squared plus y squared to the 5 halves times x hat plus y hat. And then this is, I have E written in polar coordinates here, but what this really is, and if I was to write this is E as a function of r, this is E as a function of x and y. And that's ultimately what we want to get at here. Now, like I said, the way that it's phrased, it almost seems like what it wants you to do is to plug in this r here and then take the negative gradient of this to say that the gradient is equal to x hat partial derivative with respect to x plus y hat partial derivative with respect to y, acting on this when this is written in Cartesian coordinates. But ultimately, you end up finding this, which is don't take a derivative if you don't have to. If you already know what this is, then I can just express it in Cartesian coordinates and then just evaluate it. And then that's really the same thing. Again, if there are any questions about this one, the moral or the thing to take away from this question is, how is it that I go from here to here? The other portion is, how do I convert between Cartesian coordinates and polar coordinates? It's an important thing to be able to understand that these two coordinate systems that we defined are not mutually exclusive. Any problem that you can work in polar coordinates, you can work in Cartesian coordinates, you could work in spherical coordinates, you could work in cylindrical coordinates, elliptical coordinates, hyperbolic coordinates, whatever coordinate system you want. But there's a way to go between them, and the connection between polar and Cartesian coordinates is just what I have written right here. Okay. So that was 3 and 4 from 2007. Problem 2 from 2016. And again, if you guys have questions about this, post that on there as I'm checking what this next exam is. So this was 2 from 2016. This is problem 2 from 2016. This is a good one. This is a good one. Okay. So this gets to something that actually I specifically talked about, and let me check and make sure there aren't any questions about this. Okay, yeah, we're good. This gets down to something that I talked to a couple of people about at the end of class today, when it comes to doing these problems with arcs of charge, and how is it that I'm defining r hat? How is it that I'm defining theta? Most of the time, it doesn't matter how you define them as long as you're consistent. This problem and problems like it, where it tells you that you have some charge that's spread, but it's not evenly spread. It has some function that tells you how it's spread. It's very important that when you do these problems that everything that you're doing is relative to where 0 is already defined for you. If it's a problem where it's a uniform distribution of charge, you can make a lot of different choices. It'll give you the same answer. But if you're forced into the position that says, I have some lambda as a function of theta, you have to go with the way that it's defined. Okay, so let me set this problem up, and I'll talk more about what I meant by saying that. So this one says you have to choose theta is equal to 0 up here. This is theta is equal to pi over 2, and this is theta is equal to pi. Okay, and then what it says is from theta is equal to 0 to theta is equal to pi over 2, there is a charge q1 uniformly distributed. So there's some q1 that's uniformly distributed here, and here you're given some function. Here it says that you have some function for lambda as a function of theta. So this is lambda as a function of theta is going to be equal to q2 theta divided by pi. And I also need a radius here. This is just a radius of r. So this is some radius of r. And what we want to find is we want to find the electric field at the center. Okay, so we want to find the electric field at the center. So to go back to what I had said previously, if these were just some charge q1, some charge q2, kind of the way that I had it on the homework, that are evenly spread, you could define theta however you want. But because I tell you that there's some theta or a lambda as a function of theta, the charge density varies with theta. It matters how I'm defining theta. And here it says explicitly you have to have theta is equal to 0 at the top. And what that does ultimately here is it forces you for how you're going to define r hat. So let's work on this problem, and I'll talk about that a little bit more. So the first part, let's say this is E1. dE1 is going to be equal to 1 over 4 pi epsilon naught dq divided by r times r hat, and we'll give all of these the index 1 to denote that they're different than the ones that are down here. So dq1 is equal to lambda 1 dl. Lambda 1 is going to be the charge per length here. This is some total charge q that's spread over the arc of a quarter of a circle. And so this is going to be this charge q1 divided by 2 pi divided by 4. And so this is going to be pi r divided by 2. And dl, because this is the arc of a circle, is going to be r d theta. And so this says that this is going to be equal to 2q1 divided by pi times d theta. Okay? Now r1 is going to be equal to just capital R. So now this is the important part that I was talking about. You have to choose this to be theta. So since this is theta, this is r hat 1. It actually turns out to be the same as r hat 2. I'll talk about that in a second. R hat 1 is going to have some component in the x direction of sine of theta. So sine theta 1, or it's just sine of theta. So sine of theta x hat. And then it has a negative component. So this is going to be minus cosine of theta. So this is minus cosine of theta y hat. Okay. So now I can put this all together to find what the electric field is produced by this portion right here. And that's to say that E vector 1 is going to be equal to 1 over 4 pi epsilon naught. We can plug in our lambda, so this is going to be 2q1 with a pi. That makes this a pi squared times the integral of, I need my r here as well, so this is divided by r squared, times d theta times sine of theta x hat minus cosine of theta y hat, okay? Now, the other important thing here is to think about our limits of integration. Theta starts from 0 and goes to pi over 2. So this is theta is equal to 0. The theta is equal to pi over 2. I'm not going to go through and finish this calculation. We can do the integral of sine and cosine of theta, but I want to get to the other part and to some other questions. But if this was a question on the exam, these are the types of integrals that you should do. So to look at the second part, when I'm looking at dE vector 2, this is equal to 1 over 4 pi epsilon naught dq2 divided by r2 times r hat 2. Okay. So dq2, again, is just going to be lambda times dl. The dl is going to be the same because it's still the arc of a circle. But now lambda is this function that I have. This is the q2 theta divided by pi. And so dq2 is going to be equal to q2 theta divided by pi times dl, which is going to be r d theta. R2 is R2D2, fine. R2 is just going to be the same distance that we have here, capital R. And so this is just going to be capital R. Now, here's the tricky part. Here's the tricky part. Defining this R hat 2. Because I'm forced to define my angle relative to the positive y-axis, this R hat 2 is actually the same thing as R hat 1. So R hat 2 is equal to sine of theta x hat minus cosine of theta y hat. And this might seem strange to you because when I'm down here and I'm looking at this vector that points this way, shouldn't it have a positive x and a positive y? And the way that I have this written here, I have a positive x and a negative y. In order to see that this does work out the way that we need it to, what we want to do is we want to consider what is sine of theta in the region where theta is between pi over 2 and pi, and what is cosine of theta in the region where theta is between pi over 2 and pi. So we can see this if we plot this. So if I plot sine of theta, this is sine of theta over one period, and so this is going to be pi here. This is pi over 2. This is 3 pi over 2, and this is 2 pi. So in the region between theta is equal to pi over 2 and theta is equal to pi, sine of theta is positive. So when I look at this x component, if I plug in a value between pi over 2 and pi, this is going to give me something positive for the x component, which is what it should be here, because this is the positive x-axis. The x component of this for both of these should be positive. But now let's see what happens when I plug in something between pi over 2 and pi for cosine. So if I plot my cosine, this looks like this, okay? So this is pi over 2, this is 3 pi over 2, and this is 2 pi, okay? So in the region between pi over 2 and pi, cosine is negative. So when I plug in one of those values here, that's going to give me a negative here times a negative, which makes this positive. And when we look at the y component, it has to be positive. And so that's why using this r hat 2 being the same thing as r hat 1 ends up giving me the same behavior that I need it to. And ultimately, the rest of this, this calculation is just plugging in what r hat 2 is here, what r2 is, and what dq2 is. And I've defined all of those things. Okay, so that was, I believe that was question 2 from 2016. Yeah, that was question 2 from 2016. Now the next one is, why is there an r hat but not an r squared? Oh, thank you. Thank you. Yeah. Who is that? Who is that? Garrick is the master of spotting my twos. The things that plague the physicist in terms of calculations are factors of 2, negative signs, and factors of 5. Sometimes factors of 10. But yeah, there should be squareds here. I missed that when I put that in here. And I think so far, if I'm counting correctly, you've caught 3 of those so far. Hopefully you don't get to 10 by the end of the semester. Okay. Okay, I did 2016 number 2, 2015 part 2. Let me just go through the whole thing for 2015. Is it question 2? Question 2. Okay, 2015 question 2. Yeah, this is another good one. Okay. Eyes are also a problem for physicists when we do calculations. If you miss a factor of I. Okay, so this was actually one of the problems that we had in the recitation that we worked. So let me see exactly what the question was. 2015 part 2. I think this is, tell me if I'm wrong, if this isn't the question that you're asking. Can you do 2015 part 2, we're confused on how to relate the electric field to the force with F is equal to QE formula. What would be the Q if we find E to get the F? I think I have the right exam here. So I'll just start going through this, and if this was the wrong one, just let me know. Okay. So for this one, and this tells me that it might be the wrong question, but we actually don't need to know anything about the force here. We want to find what the charge is that I have to place at the origin, so that, and let's say that this is some lowercase q, because this is some capital Q. If we know that there's some charge, capital Q, uniformly spread over the arc of this circle, what charge, lowercase q, do I have to put at the origin in order for the electric field to be 0? Okay, so this is the question. Okay, so right off the bat, what we can do is we can say that whatever the electric field is here, there's only 2 things that could contribute to it. And let me call this thing 1 and this thing 2. So the total electric field here in general, E total, is going to be equal to E vector 1 plus E vector 2. Okay. And for this very specific case, what we want to do is we want to find what the condition is such that the electric field is 0 here. So that's the sum of these is equal to 0. So we can write down what the electric field is that's produced by this and what's produced by this, and when we add them together, this has to be equal to 0. So the first one is probably the easiest one to do. This is just to find, this was some distance of A, and this is some radius r. Is just to find what the electric field from this one is. So in general, E vector is equal to 1 over 4 pi epsilon naught Q divided by r squared times r hat for point charges. So in this case, r is just going to be this distance a. R hat is going to be x hat because that's the unit vector that points from here to here. And so this is E1 is going to be equal to 1 over 4 pi epsilon naught times q divided by a times x hat. Okay, so that's E1. Let's talk about how we can find E2. E2 we need to find by talking about the infinitesimal charge, because this is something that's spread over this arc of a circle. So dE2 is equal to 1 over 4 pi epsilon naught dq divided by r times r hat. And I'm preempting, I missed one. You didn't catch me on that one yet. Okay, so this is squared and this is squared. Okay, so for this one, we need to determine what dq is, what r is, and what r hat is. So dq, just as with the other problems that we did with arcs of charge, this is going to be lambda dl, which is going to be equal to the total charge divided by the total distance that it's spread over. So this is q divided by pi r. dl is going to be r d theta. We can cancel our r's. And so this is going to be equal to q divided by pi d theta. Okay. So now we can write down what r is. For this case, r is pretty simple. It's always the distance from here to here because it's a circle. R is just going to be capital R. And the last thing we need to do is write down what r hat is. So r hat is going to be equal to, if this is, now I need to define some angles. So I'm going to define this to be the angle theta, which means this is the angle theta. So the x component here is going to be sine of theta, x hat. The y component is going to be a cosine of theta, but it's going to be negative because this is going to be the negative y direction. So this is minus cosine of theta, y hat. Okay. Now we just need to plug everything in and do the integral. And so E vector 2 is going to be equal to 1 over 4 pi epsilon naught times q divided by pi. That gives me a pi squared and a q out front. This is going to be q divided by r squared. Okay, so this is going to be the integral from 0 to pi of d theta times sine of theta x hat minus cosine of theta y hat. So over the interval for this one, the cosine of theta is going to go to 0. Again, if we look back at those plots or we think about the symmetry of what's going on here. So the y components are going to have to cancel. This is going to go to 0 when I do this integral. This one's going to give me a factor of 2. And go ahead and check that when you do this calculation. I don't want to spend too much time on the calculus, but this is just going to give me a factor of 2. So this is going to be equal to E vector 2 is going to be equal to 1 over 4 pi squared epsilon naught q divided by r times 2 x hat. This will cancel one of the 2's for this 4. And then when I add these together, they need to be equal to 0. So this is 1 over 4 pi epsilon naught q divided by a squared plus 1 over 2 pi squared epsilon naught q divided by r squared. I'm terrible about that. Okay, so q divided by r squared times x hat. Okay, and then in principle this also has an x hat, is equal to 0. So now what we can do from this equation is solve for what q is. So when we do that, we can move this to the other side. This is going to be 1 over 4 pi epsilon naught q divided by a squared is equal to minus 1 over 2 pi squared epsilon naught q divided by r squared. We can cancel a factor of pi. We can cancel an epsilon naught. we can move this to the other side. This becomes a 2 in the numerator, and then we can move the a squared over here. So in the end, we have q is equal to minus 2 capital Q divided by pi r squared, if I didn't make any mistakes. So that's ultimately what q is going to be. Squared, right? Okay, smart ass. Okay, I lost an A. I shouldn't call people out when I make mistakes. Okay. I just don't like it. It's not that I don't like being corrected. It's I don't personally like it when I make mistakes. Okay. Yeah, but you can see I lose squared sometimes, but that's just part of the game sometimes. Okay. But the process is the important thing to take away from this. And so the real physics is in saying that to find the total electric field, I want to sum the electric field that's produced by this and produced by this. And then I can find the electric field from this arc by saying that for every point on the arc, it's going to create some infinitesimal electric field here that can be given by this equation, and then we can go through the process that we always go through to find ultimately what Q is in terms of capital Q. I will say, and I don't want to give you guys too much information, understanding these types of problems is important. I will say understanding these types of problems is important when you want to say that a sum of forces or a sum of electric fields is equal to 0. Perhaps not the whole thing is equal to 0, maybe a component is equal to 0, but it's an important thing to think about if I say that what has to happen for this charge in order for the electric field to be equal to 0 here. That's an important thing to understand. Okay. So I got that question. Can you explain 2016 number 3? I hope so. I'm getting angry reviews on Rate My Prof if I can't. 2016 number 3. This is another good one. Okay, this is a good one. Okay. So this will probably, depending on the time, this will be the last one I'm going to do. But I do encourage you guys to, as you're working through these, if you run into problems, post about them on the Slack page, because I'm sure some of the problems that somebody asked me to do, somebody else had a question about it. And so part of what you can do to learn this material better is to look at the questions that other people are asking. You might have different pieces of the same problem, but in looking at what you did and what somebody else did, you can put your brains together in order to figure out the whole thing. And later on tonight, I'll be on Slack to answer some of those questions too. So this problem says a positive point charge Q1 is located at the origin, and a negative point charge of minus Q2 is located at x is equal to A, y is equal to B. Find the difference in the total electric potential at the point x is equal to 0, y is equal to 2b, and x is equal to 0, y is equal to minus 2b. Okay. So this is the setup. We have some Q1 here. We have some Q2 here. This was the point AB. So this is the point AB. And we want to find the difference in electric potential between the points x is equal to 0, y is equal to 2b. So this point, so this is 0, 2b. And x is equal to 0, y is equal to minus 2b. So difference in electric potential between here and here. I like this one already. 0 minus 2b. Okay. So in order to do this, what we need to do is we need to write down what the electric potential is from each one of these. So V is equal to 1 over 4 pi epsilon naught Q divided by R. This one, no r squared, so this is just r. And then what we can do is we can find what the total electric potential is at this point and the total electric potential at this point by finding what it is from this here, and from this one here, and this one here. Okay? Now, there's something that you can exploit here to start with. And, oh, the screen's frozen. Hopefully that wasn't too long, although it looks like it was. Let's see. Let's see. Properties. Okay, we're back. Okay, so let me go back through explaining what I was doing here, because you didn't see me set the problem up. So we have some charge Q1 at the origin. We have some charge Q2 at the point AB. And what we want to do is we want to find the difference in electric potential between the point 0, 2b and the point 0, minus 2b. Okay? And so in order to do that, what we're going to do is we're going to say that the electric potential at this point is going to be equal to the sum of the electric potential from this one, and the electric potential at this point is the sum of the electric potential from this one and this one. Now, there's something else here. You could go through that. You could go through that whole argument to find what the total electric potential is here and the total electric potential here. But there's actually a shortcut, and that shortcut is realizing that this Q1 has the same electric potential here and here. This is equidistant. In fact, if we wanted to draw some equipotential surface for just the Q1, these are the same distance. So whatever contribution that Q1 has to the electric potential is going to be the same here and here. And so when I take the electric potential difference from these 2 points, the contribution from this charge is going to cancel the contribution here and here. So really the only portion that I need is to find what the electric potential that this one produces here and what it produces here. Okay. So in order to do that, what I'm going to say is, let's call this point point 1 and call this point 2. So for point 1, this is going to be equal to 1 over 4 pi epsilon naught Q2 divided by r. So in order to find r here, what we're going to say is that's what r is. We know that this is some total distance 2b. This is the distance b. This is the distance a. And so this is the distance b. And so r is just going to be equal to the square root of a squared plus b squared. So this is square root a squared plus b squared. Okay. Now let's look at the point 2. So v2 is going to be equal to 1 over 4 pi epsilon naught q2 divided by this distance. This distance. Okay. Again, this distance here is just going to be the distance a, but this distance now is the distance 2b, and this is the distance b. And so the total distance here is going to be 3b. So this is going to be the square root of a squared plus 3b squared, which is 9b squared. Okay? And now to find the difference in electric potential, we just say that delta V is going to be equal to V2 minus V1. And then we could just take the difference between those. Okay? And like I said, you might not have noticed or realized that there was some symmetry to apply here, but all that would end up doing was you would have an extra term for both of these. You have an extra term, 1 over 4 pi epsilon naught q1 divided by 2b squared, and then plus 1 over 4 pi epsilon naught q1 divided by 2b squared. And when you take the difference between these two terms are going to cancel each other. Okay. Can we just say that you can go directly to the q divided by r, no r hat from form of the potential when dealing with the potentials between points? Yes. Yes. In fact, that's something that I would want you to do. So for instance, if I ask you to find, if I have some distribution of charge and I want you to find the electric potential here at this point, I don't want you to go through dE is equal to 1 over 4 pi epsilon naught dq divided by r squared r hat. That's complicated to do. And who asked that? It's Garrett. Yeah, Garrett. Remember, and I didn't follow up with you on this entirely. But you have to be really careful about the way that you're doing that second integral, and it needs to be with respect to this point actually being a variable. And again, if you want to talk about that later, I can go over that with you. But you have to be very, very careful if you wanted to find the electric potential at this point and then start with the dE. What's better and will give you the right answer much faster is just to start with dV. So dV is equal to 1 over 4 pi epsilon naught q divided by r, and start there. I did have my r squared. You got me paranoid now. You got me paranoid about my r squareds. But yeah, this one's r squared and this one's r. Okay. All right. Any other questions? Did I address all of these? Can you tell us how the difficulty of problems 2 and 3 compare to on 2016? 2 and 3. Problem 2 is more difficult than what I would ask, or actually what I am going to ask. Problem 3 is in the ballpark. Problem 3 is in the ballpark. Actually, no. Hold on. Which one was this? This is the charges. No. Problem 3 on a different test, I might have asked this question. But I do ask a question about point charges, and I do ask a question that is going to be related to some distribution of charge that has some dependence of theta or r, or some theta or y, or maybe both. But there's going to be some distribution of charge that's dependent on the variable that you're integrating over. But I would say problem 2 is harder. Problem 2 is harder than what I'm asking, or at least I think so. Please don't chase me back to my office with pitchforks and torches if you don't like the questions that I write. But I wrote them for you. I thought you would enjoy them. But I personally think that the question that I wrote is easier than this one, and I can't tell you now why it's easier without telling you what the question is. And I know all of you would really enjoy me telling you what the questions on the test are beforehand. But after you see it, if you want to argue with me about why my problem is harder than this, I'm willing to tell you why I think it's easier. I'll say that. Wait, dependence on both polar and Cartesian coordinates? Yeah, not both at the same time. Not both at the same time. I wouldn't. Boy, that would be something if I did something that I don't even know how I would parameterize something like that. If it was dependent on Cartesian, lambda was dependent on Cartesian coordinates and polar coordinates simultaneously. But punchline is know how to deal with distributions of charge that are along an axis, and know how to deal with distributions of charge along an arc. Those are both questions that some of the questions I came up with didn't make it into the final cut, but those were both questions that were things that I considered putting on the exam. Why is r equal to x minus a and y minus b squared? Usually not a minus x squared plus b minus y squared. Does it matter because the times the r hat? Yeah. So Pablo, that's a really good question. Let me give you an example of those two situations, and ultimately why it doesn't really matter as long as you're consistent with the way that you're defining it. So let's say that I have some point of AB here and some point XY here. And what I want to find is this distance r. So the way that I would do this is I would say that here's my distance x, this is my distance y, this is my distance b, this is a y, not an x, and this is my distance a. Okay. So this distance here, we can see is the distance a minus x. And this is the distance of b minus y, right? And so if I wanted to talk about the unit vector that pointed from here to here, what I would do is I would say there's some angle here, theta, r hat is going to be equal to cosine of theta x hat plus sine of theta y hat. R is equal to the square root of a minus x squared plus b minus y squared. And then when I replace these trigonometric ratios with the lengths that I have defined here, this is going to be a minus x divided by r x hat plus b minus y divided by r y hat. Okay, so that's what would happen if I put this over here. But then ask yourself, what happens if I move this x, y? I chose for it to be down here, but what happens if I put it over here instead? Does that still give me the behavior that I need it to have? And the question for the r is pretty readily apparent, because when I square a minus x, or I square x minus a, it's always going to be a positive value, right? It's just it's the magnitude of the difference between these two squared, regardless of what order I write them in. But this one, it is important what order I write these in per the way I'm defining this. And I can see ultimately that even if I say this is a minus x and this is b minus y, I get the behavior that I need for the situation where x is greater than a and y is greater than b when I move this up here. So when I have it defined like this, I have x is less than a. So when I take a minus x, this is a positive number. So that's going to give me something that's positive in x. B minus y, b is greater than y. And so when I take this difference, I'm going to get something positive, which is going to, again, be in the direction I need it to be, because I need something positive in y. But if I have x, y up here, still with the same definition that I have here, let's see what happens. So if I do a minus x, x is greater than a. So when I do a minus x, this becomes negative. That gives me something that points this way. When I do b minus y, again, y is greater than b. So this gives me something that's negative. And again, it's going to point in the direction I need to. So the punchline here is, and even with the r hats, when we're talking about theta, and is it going to be sine, is it going to be cosine, is it going to be negative, is it going to be positive, it doesn't matter as long as you're consistent with the definitions that you're using, and make sure that you check to make sure that it gives you the behavior that you need. So I could have said this is x minus a, and this is y minus b with a negative sign out front if I put it out here first. So let me make my definition a little bit different. This is a, b. This is x, y. And now I want the unit vector that points from there to there. So what we would say is this distance here is going to be x minus a. This distance here is going to be y minus b. But when I write my unit vector, it's going to be minus cosine of theta, if this is the angle theta, minus sine of theta. This is a y hat, and this is an x hat. Okay. So here, what I'm going to have is, I need another piece of chalk. I guess this one's okay. This is going to be minus x minus a divided by r, x hat, minus y minus b divided by r, y hat. And we can see actually that this unit vector that I have here, if I distribute the negative signs in, is the same as this unit vector. So in a very roundabout kind of way, it's important the way that you do this, whether it's x minus a or it's a minus x. But you could choose it either way as long as you're consistent with the way that you're representing the negative signs, and that it gives you the behavior that you need it to in the end. Okay? Dependence on both polar and Cartesian. Oh, I answered that one already. Garrick Oh, Garrick, you don't have to apologize. I'm just salty when I'm wrong, and it's not that you're correcting me. I just don't like to be wrong. And then that was the last one from Pablo. Okay, so that's going to be it. I'll post this right after this so that you guys can go over it again. And like I said, if you have questions, post them on Slack. I'll be on a little bit later to answer them. But also, if you see a question that you know the answer to, try to answer them, because that'll help you to think about it more. I can tell you that when I took this class, I did very well in it the first time, but I wouldn't know the material as well as I do now if I hadn't been teaching it. Teaching things helps you learn things a lot better than just doing it, because you have to think about it in different ways to explain it to people. Even what I did right here, if I was taking this class right now for the first time and you had asked me that question, I wouldn't have had an answer for it. But it's the process of answering questions that I know enough about this now that I'm able to answer those questions, and ultimately why I'm better at this material now than I was when I first took the class. Okay, so like I said, that'll be it for this session. Good luck studying, and the exam is tomorrow morning. See you guys then.